Unless you've been living under a rock, you surely saw some recent headlines that implied a stunning scientific discovery. Headlines like this and this. The planet is K2-18b, a world 124 light years away that's just 2.6 times larger than the Earth and orbits a red dwarf star within the so-called habitable zone. The signature that's got everybody excited is claimed to be that of more than 3 sigma evidence of a pair of gases, dimethyl sulfide and dimethyl disulfide, molecules that, at least on Earth, are only really made by life. A lot of ink has already been spilled about this claim with a diverse range of opinions out there, but everything that I've seen lacks the appropriate level of nuance and balance that this really deserves. So today, here at Cool Worlds, let's do a deep dive into what we really know. We'll hear from a prominent skeptic, astronomer Ryan Macdonald, as well as a proponent, the lead author of the discovery, Nikku Madhusudhan. I'll give you the facts and both sides' perspectives and let you make up your own mind. Before the recent news cycle, we already had quite a lot of data about K2-18b. The planet was discovered back in 2015 by NASA's Kepler mission, but during its second mission phase, hence the name K2. Now, Kepler detects planets by watching for dips in starlight caused by eclipses or transits in front of the parent star. The depth of that dip gives you the relative size of the planet compared to the star, and here ends up being about 2.6 Earth radii. It turns out that there are a lot of planets in the cosmos with roughly this size, but curiously, the solar system lacks one. K2-18b is in between the size of our largest rocky planet, the Earth, and our smallest gas giant, Neptune, and so we don't really know what kind of planet this even is. Rocky, gassy, or maybe something else entirely. What would really help here is knowing the mass of the planet, and so in a pair of follow-up papers by Ryan Cloutier and colleagues, they indeed went ahead and measured the Doppler shifts of the star over a period of several years, allowing them to weigh the planet as being 8.6 Earth masses. Up to this point in the story, K2-18b was largely a world only discussed amongst astronomers, but in 2019 it made the news cycle for the first time. This is when 2 teams independently reported evidence of water vapor using the same dataset, that from the Hubble Space Telescope. The 2 papers definitely pushed the data pretty hard here, but they reported a fairly confident detection, 3.9 sigma and 3.6 sigma. Now, we are going to hear a lot about sigmas in this video, so it is worth taking a beat to explain what it really means. This is nuanced, but trust me, it is important. Technically, x sigma refers to the probability of drawing a random sample that is at least x standard deviations, that's the sigma part, away from the mean of a so-called Gaussian distribution, more colloquially known as a bell curve. And whenever you do this, we call these probabilities p-values. So, as an example, 95% of random samples drawn from a Gaussian distribution will lie within 2 sigma of its mean. You get that 95% number by calculating the area under this curve, or mathematically, by integrating the Gaussian function. Another way of looking at this is that there is a 5% chance of getting a sample outside of that range. That's really what we mean by a p-value. It is a measure of surprisingness. Now, through this integration procedure, it is fairly straightforward to convert x sigma into a p-value using standard pre-calculated lookup tables like this one. But what's non-trivial is this. What probability are these teams actually talking about? Is it truly a p-value at all? Often, detections work by comparing 2 models, a null model, which is often just a flat line, and then some candidate hypothesis, in this case that K2-18b has water vapor. And if you think about it, all detections in science must ultimately come down to comparing 2 models like this. As a result, all you can really measure is something like an odds ratio between them, given the fancy name Bayes factor named after Thomas Bayes. So, for example, Benecker et al. Found that it was 459 times more likely that there was water vapor present, given the Hubble data, rather than that of a flat line, hence a Bayes factor of 459 to 1. Now, many astronomers have a curious need to convert these Bayes factors into what is called sigmas. To me, this process is both completely unnecessary and deeply misguided, but regardless, let's just try to do it anyway. And in doing so, one has to tackle a fairly deep incongruence between the two schemes. You see, Bayes factors describe the relative odds between at least two models. P-values, though, are completely different beasts. Remember that they measure the surprisingness of getting an extreme value from a single hypothesis. But statisticians have bent over backwards to try and accommodate this peculiar conversion need, and Thomas Selke and colleagues satisfied this desire with what I think is best described as a heuristic formula. But even this comes with major problems, as Ryan explains here.
Where kind of the statistics kind of becomes tricky is that one thing that's pretty common in the exoplanet literature is to take these Bayes factors and convert them into an equivalent sigma. There's kind of a problem in that if you put in a Bayes factor of 3, so odds ratio of 3, this formula will return a value of 2 sigma. And the problem there is that when I hear 2 sigma, I intuitively think basically 95% confidence. But an odds ratio of 3 to 1 is instead more like 75% confidence.
Yeah, so I mean, there's a lot of challenges and confusion here. I think it gets complicated when you talk about the Bayes factors and the sigmas. I think we go through this practice of trying to convert it for the sake of the scientific community because we think they're going to understand sigmas more easily, but I don't even think that's true. So I think let's just stick to Bayes factors because that to me at least makes the most sense because it's directly interpretable as an odds ratio between two models. So if we stick to odds ratios, remember that Hubble indicated odds of 459 to 1 in favor of water vapor in the atmosphere of K2-18b, which is typically considered pretty decisive. Accordingly, folks started wondering what this detection of water vapor meant for the, thus far, mysterious composition of K2-18b, and a provocative guess was that it could be some kind of ocean world. It's here that Nikku Madhusudhan, who goes by Madhu, first enters the story. First in a 2020 paper that explores allowed compositions for K2-18b, and then the following year introducing the Haitian world concept more generally.
Its density is too low to be a purely rocky planet. So you need a thick volatile layer on top of rock. And then we suggested in our 2020 paper 5 years ago that bulk density, the mass and radius, can be explained in 3 different ways. One is obviously the mini Neptune scenario, which was the status quo at the time. But there are also 2 other ways you can explain it, which is, let's say you just cut out the entire icy mantle part and just have rock inside. And then you need a thick hydrogen-rich atmosphere. And then we suggested a third one, which is this Haitian scenario, where you have a largely water-rich interior and a thin hydrogen atmosphere. So that was 2020 when we said, if you look at the mass and radius, all of these solutions are equally valid. But there is a chance that the habitable solution is also valid, this Haitian scenario. And that is inherently interesting. It could be just like a small percentage of all the solutions, but it's interesting nevertheless, because otherwise we don't have any habitable planets of that size to look at.
With several possibilities on the table, we need better data to distinguish. And so in 2023, JWST finally had the chance to weigh in on what was going on, work led again by Madhu. Before we discuss what they found, this video took an awful lot of online research, such as reading papers, watching interviews, and so we are grateful to Opera for their awesome Opera One R2 web browser and for supporting Cool Worlds. There's a ton of slick features here. To begin with, there is a floating music player. So, for example, you can control your music from Spotify or other music streaming platforms without interrupting your browsing. Just drag the player wherever you want, even outside the browser. And the browser itself is really beautiful to work in, with different themes to choose from, including animated backgrounds and UI colors. You can customize every aspect how you want it, such as mode, intensity, animation, sounds, colors, and more. One of my favorite features is the split screen feature. Just simply drag one tab down and you can compare 2 pages without using multiple browser windows. When doing research, I find it really useful to group connected pages into tab islands and then expand and collapse them as needed. Also, thanks to tab traces, I can easily figure out which tabs I've been most recently using. The darker the underscore, the more recently I've used it. On top of that, you've got a built-in AI tool, Aria, which again, you can access without leaving the page. Just use the sidebar or a keyboard shortcut, and that gives you access to powerful image generation and recognition capabilities. So huge thanks to Opera for sponsoring this video. You can download the 1R2 web browser for yourself using the link down below in the description. Now back to the video. Alright, so what did Madhu and his team actually do? They used a pair of instruments on board Webb that look in the near-infrared wavelengths. The basic idea here is to measure the size of the planet using transits at these different wavelengths. Any changes are then presumed to be caused by atmospheric gases absorbing at their characteristic frequencies. The team considered 11 different molecules to explain their data, molecules including water, carbon dioxide, methane, ammonia, and dimethyl sulfide, or DMS. But rather than rediscovering water vapor, as Hubble had found earlier and was generally expected, the team instead found strong evidence for methane, a whopping 5 sigma confidence, which is really quite decisive. It turns out that the water vapor that Hubble saw before was an illusion. You see, methane and H2O absorb light with a similar fingerprint in the near-infrared, and thus the teams using Hubble data had been duped. But keep this in mind, in 2019, the claimed detection significance was 3.9 sigma, or a Bayes factor of 459, and today, the evidence is gone, 0 confidence. So this is a warning shot. It shows us just how precarious these claimed detections really can be. Yes, 2 independent teams apparently confirmed the molecule before to seemingly slam dunk significance, but just a few years later, the script had flipped. Aside from methane, Madhu and his team reported modest evidence for carbon dioxide, about 3 sigma, and a hint of dimethyl sulfide, or DMS, but that was just 1 to 2 sigma. No, they don't quote odds ratios here, which I would personally prefer, but let's keep in mind what Ryan said earlier. A 2 sigma detection converts to a Bayes factor of just 3 to 1 odds. Statisticians actually have a framework for how to consider Bayes factors, and 3 to 1 qualifies as, and I quote, barely worth mentioning. So, did the media take this uncertainty into account and indeed barely mention the DMS? Now, when I read the paper, I actually didn't think that they oversold the case for DMS or anything. It was cautious, and in my opinion, they should mention it, because the alternative would be that they have this weak evidence, but they just keep it to themselves, and that really does a disservice to scientific transparency. Regardless, the media storm definitely instigated a collective sigh from astronomers, and justifiably so. Now, leaving the DMS aside just for the moment, Madhu argued that this JWST data supported his Haitian world concept, as he explains here.
If you have a deep atmosphere, you would see methane, ammonia, and carbon monoxide, and more carbon monoxide over carbon dioxide. But if you had a surface like a Haitian world scenario, then you wouldn't see ammonia, because ammonia is not only destroyed efficiently or more efficiently than methane, but it's also soluble in water. So you would deplete it very quickly. But also your CO2 will be higher than CO.
So with the ammonia, what are the current limits? I mean, do we have the sensitivity to say that there definitely is no ammonia there, or could there be ammonia there that's just hiding beneath the current sensitivity?
Yeah, so the ammonia that we have, ammonia is depleted. In other words, nitrogen, if all of nitrogen is in ammonia, then that is significantly depleted relative to all the other elements that you expect. And this is why this situation, the Haitian world scenario, is favored.
It might seem odd to argue that the non-detection of water is consistent with a water world, but JWST mostly probes the stratosphere of K2-18b, where water vapor could be quite rarefied. This happens due to condensation of water at lower altitudes within the troposphere, and that's similar to what happens for the Earth, in fact. But not everybody agreed. Later that year, a paper led by Nicholas Wogan reanalyzed the available data and found that it was also consistent with a gas dwarf after all. Now, to be clear, they do not exclude the Hessian scenario, but as Ryan argues here, it may represent a fairly small slither of the overall allowed range of possibilities.
So it could just be what we'd call a gas dwarf. Imagine you take our own Neptune and just shrink down the size of it. Or, and this is the scenario that has attracted a lot of attention, you can potentially, if the conditions are just right, the conditions allow for a surface of liquid water. And that is what has been proposed as this so-called class of Hessian planets that combine hydrogen and ocean. But a lot of conditions have to be just right. If you're even slightly too hot, you absorb slightly too much radiation, then instead of habitable liquid water, you would get a supercritical fluid.
So it's kind of like a finely tuned solution to have the Hessian world.
Yeah, and so that leads myself and many other astronomers like a priori to think it is less likely because so many things have to go right.
But the drama continues, and we've not even got into the whole biosignature debate yet, because Madhu and his postdoc Greg Cook fired back, arguing that Wogan's analysis was mistaken.
They said they can explain the composition with a mini-Neptune scenario. But if you actually look at the predicted abundances and plot the constraints that we obtain from the observations, you will find that they actually don't match most of the abundances. So there is a statement in the paper saying we broadly agree. So it's a qualitative agreement without actually comparing if the abundances match the observed abundances. And then obviously, as we do with everything else, we tried to look at it. We said, let's repeat your calculations and see if we agree with them. And to our surprise, we realized that they don't match most of the abundances. The only abundance they match is methane. And, I'm happy to be debated on this, but we want published results, right? I mean, if people can come up with a published result and show it to me, that's great. But so far, there is no published result that can demonstrate that all the abundances that we are seeing can be matched with a mini-Neptune scenario.
Whether K2-18b is a Hessian world, a gas dwarf, or something else entirely actually has no direct bearing on the recent claim of DMS, dimethyl sulfide, in the upper atmosphere of K2-18b. But where it does matter indirectly is in the context, the interpretation of what that molecule really means. Because on the Earth, DMS is produced by bacteria living in aquatic environments like marine algae, phytoplankton, and even sewers. So if K2-18b is Hessian, it naturally plays into the interpretation that DMS is being produced by life. So I think this is why this debate has become so high stakes. But really, it is just a secondary debate to two other questions that we have to address if we're talking about life here. Because in truth, the case for life on K2-18b has to jump through three hoops. 1. K2-18b is habitable, which in this case likely means Hessian. 2. DMS is present in its atmosphere. 3. If present, that DMS can only be produced by life. So clearly debate still exists about point 1, but let's now move on to point 2. Is there really DMS here? Recall that with the first round of JWST data that was using the near-infrared instruments, that indicated strong evidence for methane, modest evidence for carbon dioxide, and a hint of DMS. This is where one of my guests, Ryan Macdonald, enters the story. He's a NASA Carl Sagan Fellow working at the University of Michigan and was previously the PhD student of Madhu himself at the University of Cambridge. But what's most relevant here is that he was the second author on a paper led by Stephen Schmidt that performed an independent analysis of the original JWST data, an analysis that Madhu contests.
We've independently looked at that data, and the methane is absolutely real. So, summer of last year, when the nearest data became available, we started a from-scratch reanalysis, and what we found is that the dimethyl sulfide is not reliable. In fact, even if we take the original data and subject it to an analysis using the exact same model configuration as the original paper, the best you can say for the dimethyl sulfide is that it's indicated with a Bayes factor of 3. And that's assuming that there's no instrumental offset between the two different instruments, the NIRISS and the NIRSPEC. The best fitting model actually allows for an offset between the two. And when you do that, the Bayes factor is 1 for DMS, which indicates no evidence whatsoever. Surprisingly, we also saw that the CO2, which was supposed to be a 3 sigma detection, was at basically the same non-significance as DMS. It just went away completely.
That paper is an interesting case study on how you can create a narrative of disproving something when there is no evidence. So if we look at this, right, so they're saying, so that's our data, the black, and these are their several reductions. You can see, if you take Firefly, for example, you could see it matches the data, right?
Firefly is one of the ways of processing the James Webb data, right?
Yeah. So one of them, so all of these are different reductions, they say. And you can see at least one of them matches that peak. And that is the CO2 peak.
This is the blue points. The blue points match the black points, I think is what you're saying.
The blue points match the black points. And even without any model, that peak is what was used to claim like a CO2 inference in our paper.
But then that surely that does imply that at the very minimum, you'd have to concede, if this is true, the reality of CO2 is a reduction sensitive result, right? It depends. It's not robust to any choice of algorithm.
True. If you are having 3 reductions and they're giving you different answers, don't you want to look at what is being done in those reductions that are giving you the different answers? And I don't see any mention of that. And I don't even see a discussion of those differences in the paper. But anyway, so that is one big flaw right off. And then you go to this matrix, which people talk about a lot and, is hailed as like a very comprehensive analysis, which they themselves say. But did you know that 90% of these boxes that they show are considering the data at a reduced resolution? They take the high resolution data from which the original inference was made. And we said, we have between 2.9 and 3.2 sigma. What they do is they take that and bin it. In some cases, they bin it like up to 8 times. So just you tell me, what would be the effect of a detection significance of a data that is binned from the higher resolution?
In general, the process of binning is to lose information.
Exactly. You said it, not me, right? That is exactly what's going on.
So clearly, the original JWST data is not enough by itself to convince everyone that K2-18b has carbon dioxide, let alone DMS. And hopefully you can see from these interviews just how complex and subtle the debate can get. Different choices about the algorithms used to process the data lead to different results. There is a lot of value in having this debate for trying to understand how to process JWST data going forward. But for the purposes of this video, what we really want is decisive data either way. So Madhu and his team went back to JWST and used it a second time, but this time going deeper into the infrared using the so-called MIRI instrument on board JWST. And so finally, we get to the news cycle that we've been seeing most recently with stunning headlines and media buzz. What was your initial reaction when you saw this in the headlines? What did you think?
But my first reaction, even before I saw the paper, was surprise. We've known for a long time that there were going to be MIRI observations, mid-infrared observations of the spectrum of K2-18b. They were obtained about a year or so ago, and in that intervening time, various people had modelled and predicted what the signal strength should be. And these theoretical predictions showed that ultimately it would be very hard to detect them in the MIRI data. The error bars are much larger in the mid-infrared compared to the previous observations we had of K2-18b in the near-infrared.
So a priori, this just shouldn't be possible.
A priori, it shouldn't be possible to detect the molecules at 3 sigma significance.
If our colleagues are skeptical about the results, be it of the data or of the retrieval or so on, I understand it. Because we have been staring at this data for a year. Okay. So when I first saw it, we had like 9 months since then to really dig into it and convince ourselves, because we ourselves weren't convinced. It's too good to be true. To be able to see with one MIRI spectrum, to be able to see a feature, it's ridiculous, to be honest. Because we ourselves didn't predict it would be that strong, even in our proposal. Okay. Mm-hmm. But that's it. That is the feature that we are seeing. So now we have to contend with it and interpret it.
So let's dive straight in. This right here is the data that caused all of this fuss. The y-axis depicts the observed radius of the planet, as measured using transits, as a function of different wavelengths. That's the x-axis. And you'll notice that K2-18b appears to get a bit larger at around 7 microns, 7.5 microns, and somewhere around 10.5 microns. These apparent increases in size are interpreted by Madhu to be caused by the molecules DMS and or DMDS absorbing light at these wavelengths. It's important to note that there is a degeneracy here. The authors can't really distinguish between the two possibilities, but ultimately both of them are products of life, and so the impact is the same. Now, these dips are very subtle, raising the question how statistically significant they really are. In their takeaway table, Madhu's team quotes a range of Bayes factors, going from 17 to 1 up to 68 to 1, values statisticians would normally classify as strong but not decisive evidence. The team then convert these into sigmas using the formula that we met earlier. Again, don't ask me why. And that's where these 3 sigma values come from that you may have seen in the news. But remember that Bayes factors are odds ratios between 2 models, whereas sigmas are associated with p-values, that is, the surprisingness of getting a result assuming only one model. But regardless, these Bayes factors are very high, so surely this new data has finally convinced astronomers that this DMS is real, right? Well, not quite.
What we do when we are fitting an exoplanet spectrum, it's a procedure called atmospheric retrieval. You generate a wide variety of different atmospheric models. You explore this large parameter space and find which regions of atmospheric properties can explain the observations. If you do that in the new Murphree observation paper, considering 20 different molecules that could be there, the odds ratio, the Bayes factor that you get out, is just a little bit less than 3.
And what are those 20? How do we come up with these 20 molecules? Which is already a small number compared to the total number of chemicals that one could imagine trying.
Absolutely. And unfortunately, we only have good measurements, either theoretical calculations or laboratory measured spectra, for a very limited subset of all the possible molecules that could be there. So by field standards, 20 molecules is pretty good, actually, in terms of testing a wide variety of things. So that's definitely good. But the 3 sigma value that's being quoted doesn't actually come from the model that includes all of these 20 different species. It comes from a model that only includes 4 possible molecules: methane and CO2, and then DMS and dimethyl sulfide. So the model was down-specialized before calculating the Bayes factor, which increases the Bayes factor from 3 to about 20, which then maps onto this equivalent sigma of 3. And intuitively, the reason for that is that DMS and this other kind of like DMDS have strong features, much stronger than methane or carbon dioxide, when you go to wavelengths longer than about 9 microns. So essentially you've removed other things that could explain absorption in the mid-infrared. So of course the detection significance will go up. So many of us have kind of concerns that this is overstating the statistical significance of what we can actually say.
So I think this is the biggest criticism I've seen kicking around. When you did your initial model, which you call the maximal model, you tried 20 molecules, and including within those 20 are DMS and DMDS. And when you turn those on and off, that difference gives you a 2 sigma number. And then you kind of hone it down. You say, okay, like the rest of these other molecules, there's no evidence for them, so why are we even including them? Let's strip them out and get just down to the 4 that we really think are active and repeat this test. And when you repeat the test, then you get 3 sigma. And I think maybe the statistical criticism would be you've kind of double dipped on the data a little bit, right? Because you've looked at the data once and you've used that to define a prior, and then you've gone back and refit things again. So what is your response to this?
Oh yeah, no, I'm very, very glad that you brought this up, because people don't know the context of this, right? So I can tell you that this is like the most comprehensive analysis of a Murphree data set that has ever been done for exoplanets upfront. And to justify that, you'll have to know what else has been done in the past. So this was a paper just from late 2023 using Murphree exactly the same instrument that we are using right now, JWST MIRI. Okay, so let's see what exactly have they considered for the molecules. There are 4 molecules, 2 atoms. So what is the justification for considering those 4 molecules? So now you tell me, when you're asking this question, why did you include only like a certain number of molecules in your final retrieval? Well, that's because that's a sensible thing to do. And it's better than what has been done before. And I'll tell you one other thing, we can come back to this later, but with all of this, right, all the analysis they've done, look at the title, quartz clouds, right, in the atmosphere. What is the significance of it? It's a 2.6 sigma significance. So there was a press release for that. This, because we are on the topic. So this was the press release. Can you see this? What is the phrasing? Webb detects quartz crystals. And that was 2.
So you're saying there's a double standard, right? I guess is your point. Yeah.
There is a double. It's a 2.6 sigma inference with a limited set of species, and you're saying it's a detection in the title of a press release. There's no mention of what that detection significance is or what it means in terms of content.
Yeah.
No,
I totally hear you. Although I think whenever you talk about life, you have to expect greater
Absolutely.
skepticism, Madhu.
Absolutely.
I mean, that's just inevitable.
Absolutely. This is why we never even said we detected it, right? We're saying hints. So there's a big difference, like in how we're putting it. But that is all besides the point. The point to your question is, how many molecules do you include, right? What we did, let's take the molecules that have been predicted in the literature. Let's add several more molecules. Let's have a big set, 20 molecules. And then we said, we are picking up only 2 molecules at best, DMS and DMDS. But let's also include 2 more molecules that we have inference, we have evidence from before. So let's include them for completeness. So we included 4 molecules and then did like a full thing. Now, you give me a good reason to include another molecule, I would include it. And if the detection significance changes because of that, and I'll own it. But you construct a model based on what is most reasonable. And this is the most reasonable approach that has been done in the field to date. And
yeah, I want to be sympathetic to this, that I do think it is double dipping on the data. I do think that's true, but I'm sympathetic to it because what else are you supposed to do? I mean, it's almost like there's trillions of molecules. So really your maximum model should be a trillion chemicals, and then there'd be no significance of anything ever if everyone did that. So you have to cut down to something, and that's always somewhat of a subjective choice. And we can argue about that subjective choice, but it has to be made. There's no way around it as far as I can see.
Yeah, and more importantly, from our perspective, is that we have to stick to existing standards in the field. Right? We are not inventing anything here. We are taking exactly what was done before. As I showed you, it was a big, NASA press release. We took that as our benchmark and upped it in the sense that instead of assuming something, let's look at a much larger set and make an informed choice on what we are building.
So I wanted to show you both sides of this argument in the interest of balance. As I said in that last clip, I do think there is a double dipping issue here. The team tested 20 molecules on the data, found evidence for only 2 molecules using that data, and then used that to refit the same data with a smaller set of molecules. That's statistically forbidden. But at the same time, I have to concede I don't really have a better solution. Because rigorously, there are over 10 million known molecules, so arguably a comprehensive model would include them all. Leaving aside the practical concern that we do not have spectra for the vast majority of those molecules, attempting to fit any realistic JWST data with over 10 million free parameters would be an exercise in overfitting. You would never detect any molecule that way. I think these questions really highlight how, like with most frontier research, there's no textbook telling us the best way to do this. Scientists are forced to devise the methods as they go along because they're often treading in virgin snow. And we can certainly look back and critique those choices and hopefully improve our methods next time around. But fundamentally, science is an iterative procedure that's baked in. So, does K2-18b have DMS? I'm going to let you make up your own mind, having heard both sides. But here is some food for thought. Often, the kind of people who become scientists do so in part because they want to make significant contributions to scientific knowledge. There's a hunger for that in all of us. And so, As we don our wax wings and fly as close to the sun as we dare, squeezing the data ever harder, there is an inherent risk that this ambition will sometimes cause us to overreach, like Icarus. But at the same time, science is a highly competitive environment, and so you will rarely see rivals celebrate another team's success. Our biases often drive us instead to try and poke holes in their analyses. And in a way, that's good, because scientific truths are those that survive broad and intense scrutiny. They are the irrefutable facts that even the most ardent critics cannot deny. But it has to be said that there is a certain sport to it too. It's easier to destroy something beautiful than to craft it. Two things are certain though. First, other teams will produce independent analyses of this data. Now, if they disagree with Madhu's work, they will likely get published and make a lot of noise. However, if they agree with Madhu's work, it's less obvious to me that you'll hear about them, because there is definitely a publication bias towards refuting provocative claims rather than simply reasserting them. Second, barring some disaster to JWST, K2-18b will be reobserved, and in principle, even a few extra transits will provide conclusive evidence either way. Given that the planet takes just 33 days to orbit its star, there will be plenty of opportunities for this. Finally, what if we get to a point where everybody agrees that DMS is in this planet's atmosphere, and further, that it is indeed a Haitian world? Does that then equate to the detection of life? Now, yes, on the Earth, DMS is primarily made by life, but it was also recently detected on the dead comet 67P. Now, Madhu is well aware of this paper, and he points out that it seems implausible that comets could ever deliver quite as much DMS as K2-18b seems to have, but it establishes a counterpoint. Clearly, DMS can be made in at least one other way that we don't yet understand.
There's a lot of skepticism and unknowns about whether DMS or DMDS can actually be a biosignature. And the problem is that this is a very different context, this planetary atmosphere, versus what we know from the Earth. And if you want to establish that a molecule that's detected is a biosignature, you have to be very confident that you can't produce it abiotically. There needs to be laboratory experiments. There needs to be theoretical calculations so that we can rule out that photochemistry can't produce it. You can easily produce sulfur-bearing species via photochemical reactions, much like how ozone is produced in the upper atmosphere of the Earth. In short, there's a huge amount of work that would be required to establish if DMS can be a biosignature in K2-18b's atmosphere. But it's just incredibly exciting that we can even have these conversations, and we're all very excited to see this work being done.
I have to point out that there was also a certain irony that the very next day after Madhu's paper came out, his old PhD advisor, Professor Sarah Seeger, posted a paper arguing that there is no such thing as any single molecule which could ever be used to prove biology. No silver bullet.
I just don't know if it's really a sad thing to tell you. I'm sort of growing awareness by this work and other work that there probably is not a unique biosignature gas out there. And I'm personally still coming to terms with all of this.
So there is a lot more work to do here. Lots of reanalyses, more observations, lab experiments, and theoretical calculations. But despite all of that very appropriate cold water, the fact that I am even making a video like this is kind of ridiculous. We live in an age where our telescope data is plausibly sensitive to alien biology. I mean, just think about that. That is wild. So I'm going to let Madhu have the final say on this video and try to sum it all up for you. So until next time, stay thoughtful and stay curious.
One of many things can happen, right? The signal may not be real, which is fine. We may have missed something. As robust as we think we are, we may still have missed something in the data reduction. Someone may come up and say, fine, it's different. Sure. So the signal may go away. The signal, it could be something else. So someone else may be able to do a retrieval and say, actually, it's not DMS or DMDS, it's some other molecule. Now that would be good too, because that would be a discovery of a new molecule. Because so far, any molecule that people have claimed it and is in the retrieval, we don't find it. But if someone comes up with something else, that would be a big deal as well. But that should also be robustly tested, obviously. So any of these possibilities I'm okay with, but what I'm most excited about is that we have anything at all to try. And that is the huge deal we are talking about, having a blip. And most people lose this point, that the fact that we are having anything of a blip on a habitable zone planet is out of dreams. Even I myself, who is like head to toe involved in this field for the last 2 decades, would never have guessed that we would be there at this time.
Thank you so much for watching, everybody. I hope you enjoyed this one. Let me give a special thank you to Madhu and Ryan Macdonald for generously giving me their time and making this video possible. Couldn't do it without you. And let me also thank our latest 2 donors to the Cool Worlds Lab. That is John Morrison and Ben Kingston. Thank you so much for your support, guys. If you too want to become a supporter of the Cool Worlds team, then you can use the link up above and down below. And until next time, I will see you around the galaxy.